Hello everyone, welcome to the GeekNet podcast. I'm your host Kaivalya Apte and I am back with another episode on this podcast. Today we are going to talk about distributed SQL databases, what they mean, why do we need it, and understand CockroachDB in depth. To do that, I have Jim Walker with me from Cockroach Labs, and he's a principal product evangelist at Cockroach Labs. And he's going to help us understand the world of distributed SQL and CockroachDB. This is going to be very technical and very developer friendly. So stay tuned and consider subscribing to this channel. With this, without further delay, let's welcome Jim. So, Jim, let's start with a little bit of introduction about yourself, what you do at Cockroach Labs.
You bet. And first of all, though, thank you for having me. I'm happy that you asked me to be on. I love talking about this stuff, and I love what you're doing here with the podcast. It's really great. But and then also, I'm going to call you KV just because it matches up with what we're doing in Cockroach, like way down in the storage layer. But we'll get into that later, right? So thanks, KV. Y'all, I'm Jim. I'm Jim Walker. I am as noted the principal product evangelist here at Cockroach Labs. I've been with the company for about 3.5 years, almost 4 actually. I think I'm only like 2 months away from being here, 4 years. But I was first introduced to CockroachDB, I would say about 5 or 6 years ago. I was at a small company called CoreOS. It was container Linux. It was like early on in the Kubernetes community, whole thing. And we were looking for an app to run on top of Kubernetes. And I saw Cockroach and I couldn't unsee it. It's kind of like when you see a cockroach in your apartment, I guess, in New York, like you can't unsee it. So I've been with the company for really quite some time. Now my career has been in startups. This is my 10th startup in a row. And it's always kind of in emerging technology, technology that people don't totally understand yet. And so I've always prided myself in being able to take fairly complex topics and actually complex, let's just say very technical concepts. And I try to explain them in a way that's consumable for everybody else to understand. So I think this is going to be a test in that today, KVs, but I'm looking forward to it. I hope I do a good job.
Awesome. Yeah, I thank you for being here and giving your time for this podcast. And as you said, we'll try to break down those technical, like complex topics into simple, easy to digest ideas. So let's get started. Before we do that, I would like to understand a little bit more on the role. Like I've seen very recently that evangelism, like developer
Mm-hmm.
relationships and product evangelism, is the new thing, right? So what it takes to be like a product evangelist?
You know, I think there's a couple things. I think a deep understanding of the technology is number one.
Hmm.
I think you can't really, do what you do as an evangelist without a fairly good, a deep understanding.
Yeah.
You need to be curious. I think is one of those things as well.
Mm.
And I think you need to be passionate about these things.
Yeah.
I think all those things come together. I was originally a developer. I have a computer engineering undergrad. I coded for years, and I eventually became a product marketer. And a product marketer really sits between the market and the product and lots of different things in a company. And recently, I've moved into this role as more as an evangelist. And what I've realized is that you sell products, but you evangelize belief systems. And that's a kind of this word I've been kind of explaining in my new job because I believe in this stuff. Like I believe that the database has to change over the next 5 years.
Mm.
I believe there's a better way of doing all these things. And so for me, being an evangelist is a way for me to kind of use my passion and use my curiosity and my understanding of the product in a way that helps, hopefully, the people listening today, they become believers as well.
Mm.
I'm not selling a product here. I just truly think this stuff is awesome. And I think it's great when people understand it, right, Katie?
Yeah.
And so, for me, evangelism is very different than the marketing side of my life and what I've done because I was selling something before. And I think I was always kind of an evangelist in that world. But in this role, it's really about it's letting people see what the future needs to be. And hopefully they believe and walk to that with you. And I think it's a whole lot of fun for me.
Yeah, very interesting. So I think this also closely aligns with what we are doing on this podcast, like being curious, sparking that curiosity on technical topics, and although like being difficult technical topics, we are able to discuss them in simple manner. So I think that's what is, product evangelism all about. So all those people who are listening to the podcast, who are watching our video, if you wanted to become like an evangelist, this is what you need. So thanks, Jim, for sharing that. So let's get started on our topic. As I initially mentioned, we want to discuss on distributed SQL and CockroachDB. So let's start. Before we dive deep into that, let's start with a little bit on history of databases from your perspective, right? So we had this traditional relational SQL databases, which with beautiful ACID transactions and with one machine serving all your data. But then there was some issue, and then we began with NoSQL databases. But here we are today with distributed SQL. So what is the history of databases from your perspective?
Yeah, that's a whole topic in itself, buddy. So, I mean, look at, the database goes way back to, 1970, 1972, IBM, the relational database is born. We were really looking for a way to kind of simplify how do you take data and store it to disk in basically a reliable way and a consistent way. And I think what happened over the next 15 years from that moment in time was, we developed these kind of, algebraic and calculus type math. We applied math to the problem. And, the concept of the relational database really kind of came out of that, and the emergence of this SQL in the relational form and data modeling and cardinalization of queries and normalization. These are all kind of topics that you learn in kind of database management class.
Yeah.
I think when I went to school, that was like a required course. I don't even know if it's required. I don't even know if they teach relational databases anymore, but that was required. And I remember like, the normalization part of things was like, it was all math, right? And so like, this concept of this relational database has been around for really quite some time. I mean, in the mid 80s, Oracle and Larry and this team, took it a long way, and they really kind of started to drive it as kind of the standard way in which businesses were going to interact with data. And that was really the beginning of that. It's like really that mid 80s, early 80s. And then, at the same time, Ingress was a company back then. This guy by the name of Michael Stonebreaker broke off of Ingress, and he created something called Postgres. And so Postgres has been with us for dozens of years as well. Yeah, it's amazing. And what an awesome, like in the history of open source, like Postgres has to be probably one of the coolest pieces of software ever created. I mean, and it has been around for a long time. And what the beauty of this is, like it's all built out of the same kind of algebraic form, right? And Postgres really started to take hold in, say, the mid 90s, and you saw basically Oracle kind of accelerate up. Sybase kind of went a little weird, and then Microsoft SQL Server came along. All the while, DB2 has been there. Yeah. And so if you look at our lives today, like since you've been awake this morning, since I've been awake this morning, I'm in London. It's 8 a.m. I'm sorry, I was on the internet at like 3 in the morning because I had a little jet lag. But you've probably hit a relational database 20, 30 times without even knowing it. Like your life is, and our lives are running these things. Interesting enough, fast forward about into the early 2000s. And if you really want to see what's going on in tech today, and I tell everybody this, go investigate and be a student of the history of Google, and look what happened at Google. And so around I think it was 2004 timeframe, Google invented something called Bigtable. Yeah, and Bigtable was the inception of NoSQL. And if you really want to follow Google and everything that's happened, there's two engineers at Google, Jeff Dean and Sanjay Gemawat. And the two of them together, I don't know if you've ever talked about it before on the show before, KV. Has anybody ever mentioned them?
No, not really.
Oh, dude, they're amazing. Like these guys, like the innovation that they have given us as software engineers, beyond. Yeah. It's beyond. Like it is like TensorFlow is them, like MapReduce and Hadoop is them. Spanner, which I'll talk a little bit about here, which is kind of the advent of distributed SQL, Bigtable. Like if you just look at like the scholarly articles by Jeff Dean and Sanjay Gemawat, incredible. And what they were trying to solve for was like they had these relational databases, but they needed this scale thing, right? Because Google Google had figured out that, like, look, at the search engine thing is cool. It's a feature. What we want to do is basically provide, data to everybody on the planet in real time in ways that just hasn't been done before. And they basically said, let's look at the database. Let's take off the rails of transactions, and let's take off all the, the primitives of, referential integrity and some of the things that hold back the performance of getting data everywhere. Let's take that out and let's create something different. And that was the advent of NoSQL.
Yeah. And
NoSQL has been around really for, it's about almost 20 years as well now. And, we saw lots of NoSQL databases come about, and it's been great for us. I think the freedom of the data model, like taking off these constraints and having this agile data model in the NoSQL database, has been phenomenal, and it helps us do certain use cases. Yeah. But the relational model still applies in many ways. And so, we're going to live in this world where there's different databases for different problems, and that's kind of really how we got here. I just to round this all out. I just think that the relational form of data, the relational database and SQL, is the language of business. Yeah. And if we think about NoSQL and kind of where that's been and how is this actually gonna is this gonna take over the relational? I don't see it. And if you want to investigate it a little further beyond kind of operations and transactions, we have to kind of get into kind of what's the language of analytics. What is the first thing that people do when they're kind of investigating their data? Yeah. And I think people think about and want to actually kind of walk through their data using SQL, because it is the language which we use to actually interact with our data.
Yeah, thanks, Jim, for that answer. And I really agree that SQL is so beautiful. It's declarative. It has this less learning curve, and anyone can write and learn SQL. And relational databases or relational model itself is so easy to understand and easy to reason about that it makes a lot of sense to what you said. But with this, I want to dig a little deep into the problems that we faced with relational databases. So we had MySQL, we had PostgreSQL, and we wanted to distribute them. So we could always shard them, right? So what is the problem with having these shards that the modern distributed SQL databases try to solve?
Yeah, it's I think it's a little bit more than that, actually. I mean, I think the beauty of the relational database is we put a lot of power into it, like being able to do joins and aggregate views and strong data typing, and think about like just referential integrity, and think about like one-to-many and relationships. And there's so much power in the database that we don't have to code for anymore. Like, yeah. The beauty of that is like, that's great, Unfortunately, like these databases were designed for a single server, sat underneath your desk, right? Like that's what it was defined as. I mean, back in the, in the 90s when I was, architecting solutions, it was like, great, we would go and figure out, how large of a database we're going to need. We go pay a database vendor for that database, and then whatever money we had left over, we spent on the largest, machine we could find. Yeah. To get the best performance out of that. We still maintained our own machines and we served data, and that's all changed. I mean, we've lived in a world where relational databases have worked for a long time. They're amazing. But when we need to scale them, we have two choices. Yeah. Right. We have vertical scale, put a bigger box in, or we have horizontal scale, shard the database and put it over multiple servers, which adds complexity. It's difficult to maintain. The operational overhead goes increasingly up exponentially with the more of the shards. The other side of it is how do you survive the failure of this thing? Like this whole concept of this active passive system, having a primary and a secondary. When the primary goes down, the secondary comes back, and how do we like those two problems? The operational overhead on these databases has been something that's difficult, but I think we've just lived with it for years. We basically said, look, that's how this works. Okay, great. Like, and we've made it work, and there's a lot of different technologies out there that have made this even better. Like, I think there's things like auto sharding, like Citus did that. If you look at the test project, like we're doing kind of automation of sharding. Is that distributed I think distribution is about being distributed at all the layers of the stack. And
Yeah.
in the advent of distributed SQL, again, I hate to go back to Google, but it just does, y'all. Like it really does. I mean, they had Bigtable.
Yeah.
They had figured out how to get data all over the planet and make it available and have kind of broad distribution.
Yeah.
But they needed transactions. And when I talk about transactions, everybody talks like, "Ooh, ACID transactions." I'm talking about like, strong ACID, strong guarantees. Like the I in ACID is what's important, the isolation level, which 9 out of 10 developers have no idea what an isolation level in a database is. And that's okay. Like, because it seems like a performance tuning, like change I make, but like actually it's a big deal. Right. And so like putting the guardrails back on this broadly distributed database is really kind of the advent of distributed SQL. And that's where that came from. And so I think the like distributed SQL to me is really about not just automating sharding. It's not even sharding. It's about distributed consensus. It's about distributed execution of transactions.
Yeah.
It's about distributed storage, because ultimately every database is made up of 3 levels. There's 3 layers in every database.
Yeah.
KV, and it's the language, which I really believe in SQL. Like I don't know, dude. I think I gave up on the document model somewhere around like XML. I don't understand. Like I think like normalization, dude. I think in ERDs, like, so there's the language, right? And so, I'm sorry, that was a pretty strong opinion. Sorry. But like, there's a language, how you interact with something, right? That's number one. And at the bottom of it, it's a storage layer. How do we, because ultimately a database is nothing but, I mean, really, like every database is basically the other side of what a user wants to do. Like your application is just the stuff that sits between a user and a database, really.
Yeah.
And the database is really about storing data to disk. This middle layer is actually what's really important to me in distributed databases, and it's distributed execution, and that's really difficult. Because when you start to actually have truly distributed systems and distributed execution, and this goes beyond the database, this goes into what we're all doing, like as we get into microservices and kind of these broadly distributed systems, it's a mindset, and it's a really a different way of looking at the problem. And so like for me, to truly be distributed SQL, being distributed at all those layers and like thinking about like, what are the changes to the language? How do we store the data differently? How do we execute transactions differently? To me, that's the advent, because that's what truly gets us out of this active passive resilience into active. How do I make everything active? How do I make every single node an endpoint, and you can connect to any like that's distributed systems. Sharding, what like no man, nobody. I've never met a person in my life who ever really enjoyed sharding a database. Maybe somebody in the geek podcast out there maybe likes it, but like no, like just like that just happened, right? And so. To me, it's distributed is like it's a complete paradigm shift. I've landed on the other side. I'm not sure every other database has landed on the other side, but I think we're all moving there.
Yeah, that makes a lot of sense. So to summarize what you said, I think it's not only about the sharding of data, but being like support the distributed concepts in a database natively and at all layers is what matters. And that takes away a lot of complexity from the application developers to the database back as it was in back in the day, right? So that makes sense. And with this, I think it's time to dive deep into distributed SQL, how it works, and we are going to take CockroachDB as an example because that is one of the leading distributed SQL databases. I've also read a bit about it, but let's start with the history of CockroachDB, right? First of all, why it is named a CockroachDB? Is it related to the cockroach? Like, and I was just reading, and it seemed like it is related, but I would like to hear from you.
Yeah. So the story starts in really in the early 90s, honestly. Like, funny enough, like Peter Mattis and Spencer Kimball, 2 of the founders here. Ben Darnell is the other founder. Ben is maybe the best programmer I've ever met in my life. Like, he's incredible. All 3 of them, incredible developers, engineers, I should say. Peter and Spencer went to Berkeley together. And have you ever heard of the photo manipulation tool called GIMP?
No.
so this is open source like Photoshop kind of thing,
Okay.
right? And it's been around forever. And I'm sure people here have heard of GIMP. Peter and Spencer actually built that in their dorm room way back. And so they've been friends for a long time. They both landed in Google in the early 2000s. They were all within, and Ben as well, they were all within like the employee 300 range. I know Spencer and Peter were working on Colossus, which is the backend file system of Google. Ben worked on Reader, which was a beloved, project that, Google sometimes gets rid of great products. Ben worked on that. They all left. They went to, it was Square. Yeah, I think it's Square. And they were basically tasked with they started a company. They were frustrated with tools. They were using databases. They had this kind of operational overhead. They didn't have that Google, because you talk about distributed databases making this easy for the developer. I think the developer just wants a language that's beautiful and they just want SQL. They don't care about all these other things. It's the operators and the architects who have to actually make these things scale. Yeah. And so they were tasked with they were tasked with being SREs, man. And they were like, this is horrible. And so they didn't want to do any of that. And they were like, man, this is frustrating. And so they had a photo sharing site. It got sold. They were working in a larger company. And they were like, well, let's just try to build they were inspired by what Spanner did. And so they just started building. And so, one night when Spencer created the Git repo, he's living in New York City. There's the ubiquitous Cockroach. And he was building a database you can't kill. And so they ended up naming the database Cockroach Database. Yeah. So on a whim, where it seemed like kind of a funny name at the time, here we are, that was, I think, 2015, 2014, right? Here we are 7-8 years later. And there's a company named Cockroach Labs. So funny name, but I think, love it or hate it, I don't think people forget the name, so
I find it
cool. It works.
Yeah,
it's cool.
I found it very cool. And also the reasoning makes a lot of sense. That's behind the idea of CockroachDB, right? As you said, it's impossible to kill. And I was also reading some blogs on people who are actually using CockroachDB. I think it was from Bose or someone, and they said that we tried everything to kill this database, and it was not possible. So that talks a lot about the database. But
really quickly on that point, KB, and I'll tell you something that's really interesting about this database and this its impossibility to kill it. In a lot of the large banks, like the huge, massive banks on the planet, they have security problems, right? And so what they do is every month or every 2 months or every 3 months, they basically repave an entire machine. Basically kill the machine, kill the operating system, just repave the entire thing from bit zero all the way up. And they do that. And it's, oh man, it's all hands on deck. Everything can go wrong, but they have to do it, right? To make sure everything is up to date. Yeah. The team that actually deals with the Cockroach servers, they're given 3 days to do, and they kick back, because they're okay, we repaved it, and the cockroach is back. You can't kill it. They're just and they're doing it without downtime in production. Yeah. And so this concept of being able to survive anything, because you know what, there's planned downtime and unplanned downtime, dude. How do you upgrade a database and that sort of things? And so there's another one of our customers. I was asking hey man, what happens in the middle of the night when the problem? He's like, I don't care about when there's a problem in the middle of the night. Yeah, it's when there's a problem in the middle of the day and everything's going on, and I have this interrupt processing, and that's all hands on deck to fix the database. And so being able to get past that, and this being able to survive any failure, an a rack going down, an AZ, a whole region, because man, regions of cloud providers go down. You know what I mean? So that resilient nature is a big deal. Sorry, I love those two stories, and I think they're demonstrative of wow, that's kind of cool, right? So yeah,
totally. So thanks for sharing that. I was just saying that we are going to get a little deep into how fault tolerance works in CockroachDB a little bit later. But before that, let's understand what is CockroachDB and what is its relation with Spanner.
Yeah. So we were inspired by the Spanner white paper. Again, I got to say, man, kudos to Google. Google publishes all these great papers. You can go read the original Spanner white paper. Anybody here, like, just go to the scholarly articles. It's great. It's awesome.
Absolutely.
Amazing. And so we were inspired by that. It's a very similar architecture. Now, what Spanner does, and we'll get into distributed transactions a little bit later. When we talk about transactions, like the clock, the time, I don't know what time it is there, KB, on your desktop, but on mine right now it says 4:11, which is basically, I think it's like New York time.
Yeah, it's New York.
But I don't have milliseconds here. You know what I mean? But like when we're dealing with distributed transactions, and I'm trying to commit something here, and you're in Germany, and I have a third version of it in New York. New York, London, Germany. Okay, our machines like synced up so that we're on the same time. It's a big deal.
Yeah.
Google does this by using something called an atomic clock. And I'm sorry if I'm going deep already, but like they use hardware to do this, which basically is really cool. We wanted to do it in a way, and the founders wanted to do it in a way that wasn't tied to particular hardware. How do we build this in a way that's going to be usable on every cloud provider, on every machine, anywhere, like be very truly open to running on anything? And that was really kind of the advent. And so we were inspired by Spanner. Now, distributed SQL to me is really about a relational database in a distributed form. Mm-hmm. It's taking distributed principles of being active, and always on, and available to as far as you possibly can, and applying it to the database. It's I know we were talking about the CAP theorem at one point, but like how does that apply to the database and kind of what we're trying to do here? And so I think to the developer, distributed SQL is just a relational database, and that's what it needs to be. It needs to just be the relational database. Like you have Postgres, it's Postgres but better. It's take away the operational overhead of sharding the database. Let's give our systems business continuity of being always on available. But then I think most importantly, and the most difficult requirement to deal with is being able to confirm and deliver high performant, low latency transactions, no matter where that database lives, and no matter where nodes live. That's a difficult problem to solve. And I think those are the three things: it's scale, it's resilience, and it's kind of this locality and understanding where things are.
Okay, sounds good. And so when I was reading CockroachDB, it felt like it is the silver bullet, because what I read is CockroachDB is this distributed SQL transactional database supporting strong consistency, serializable isolation, geo-replicated distributed data, and highly available, highly fault tolerant. And these are a lot of buzzwords, and implementing those and being true to it is really difficult. So let's get a little deep into the CockroachDB's architecture. So how does it look like if I have to, just look at some boxes that comprises the CockroachDB?
Yep. So as noted, right, there's the storage layer. How do we store data? So at that layer, we think about distribution of data and replication of data. Those two things. And we'll talk about replication of data when we get into distributed consensus and Raft. In the middle layer is this execution layer. How do we distribute execution? It's kind of like, if anybody's familiar with like MapReduce, how do we map and reduce back and really have execution happen in many different places? And then at the top layer, it's the language. It's SQL. And so what are the things that you have to change to SQL to make it distributed? How do you, like we were talking about, like location of data and where it lives. How do you make these concepts kind of native primitives to the SQL language? Because there's things you have to add to take advantage of this. Because the trick to distributed systems, in my opinion, and I've maintained this for really quite some time, the minute I got past my hurdle to understand distributed systems, because I come from I've been doing this for 20 years, I come from like the traditional world. For me to really start to understand distributed systems, it's when you start to apply the physical layer on top of the logical model. And if you really think through what that means for yourself, like you start to think differently. And that physical layer, like distribution, how many times I'm writing, replication, where it lives, right? Execution, distributed, where does that execution need to happen in this distributed system?
Yeah.
And then at the SQL layer, how do I actually communicate with the system to understand where data lives too? Because to me, distributed systems is about applying the physical layer of data or physical layer of the world to our logical model that lives within the bits and bytes of our machines.
Mm-hmm. Yeah, and I think that's a great mental model, like thinking about these layers and these terms into like how the data is distributed, what it means by replication, and it makes it a lot easier to understand these concepts. With this, let's see how it works. So let's say, so as a developer, what I see on CockroachDB is a simple, let's say, SQL UI, right? And I write my SQL query, like insert something into the database, and these are the columns, and this is the data. How does this insert query gets converted and ultimately makes it up to the disk?
Yeah, so it's funny. Usually, when I describe this, I come from the bottom up. I come from storage to the language, and so let me do my best to come down.
Yeah.
Because I really think that's what helps developers understand. Oh, wait, this is really different underneath, but I don't care. Because you know what? I'm insert KV. I hate to use your name because we're going to actually talk about that at the bottom layer. Insert like Kavaya into customer table, right? Like, and so what does that mean? Yeah. Well, when I insert that, it's going to insert into like to you, it's just okay. It was transaction committed. Thanks, developer. Great, awesome. You know what I mean? And like underneath, though, a lot is happening. So when you write data to Cockroach, what you're doing is you're actually writing data some odd number of times: 3, 5, 7, 9, 11. Right? Some odd number. And we use something called distributed consensus. And distributed consensus, like the algorithm we use, is called Raft. And if you're not familiar with Raft, go check it out. There's a website called The Secret Lives of Data, all one word, thesecretlivesofdata.com. Great explanation of Raft. I've sent, thousands of people to the site. Really, really great explanation of Raft. But Raft is distributed consensus. And so typically when you thought about like pushing data all over the planet, you would write to one node, it would commit it, and then asynchronously you replicate data to other places. We don't do that. What we're doing is we're saying, like, let's write the data an odd number of times and then get a quorum right. So we get a quorum acceptance of that. So when I say insert this record into the customer table, it's actually going to write it 3 times across 3 physical different instances of the database, right? 3 different nodes.
Yeah.
And what it's going to say is like, as long as 2 of 3 of those come back as committed, great, I'm good. Because I have quorum, 2 of 3 or 3 of 5. Or 4 of 7, right? And it depends on your replication factor, which is a setting. Now, by default, Cockroach databases, the replication factor is 3. And it's sufficient for most of the use cases. Sometimes people want a higher level of replication. And that comes back into like what you want to actually do in terms of what do you want to survive. And if you think about this, okay, so I've written the data 3 times. Okay, so if one node goes away, like it dies, well, I still have 2 of 3 of those copies. And so what Raft does is it basically says, like, look at all times, do I have all 3 copies and are all those 3 copies synced? And so the algorithm, the protocol is actually just doing that for you. And so that simple instance of a write is saying, hey, look I've done this. Now in Raft, there's and if you, like I said, if you look at that website, it's great. There's a special concept. And so what I did is I wrote it 3 times. And so I'm writing this data 3 times across. We'll get into the storage layer a little bit. But there's something called a Raft leader. And the leader basically has kind of this authoritative, up-to-date version of what's going on within this replica set, these 3 versions, right? And that Raft leader also helps us kind of get atomic kind of commits. It's like, hey, did this happen or not? Like, we always talk to the leader, and the leader's like, yeah, we're good, But the leader also understands if like the 2 followers are still there. Like, what if one of the followers died, that node? It would know to create a 3rd version of that data somewhere else, right? So that you're always guaranteed to have these kind of 3 versions of this, right? So Raft and distributed consensus is a critical part of what we're doing in Cockroach Database. There's a lot of other stuff when we get into transactions we can talk about. Paxos is another one of these algorithms that's helped people doing this. But the real difference there, and to the developer to actually understand, is I'm writing data 3 times. And so what does this mean for the developer? Well, if something goes offline, or like there's a say there's a conflict, right? You may have to retry your transactions.
Yeah.
And that's one of those things. And so, like, to the developer, what does that mean? Well, I got to put try catch blocks around things. This is something I was horrible at as a developer. But this is kind of one of those those things you kind of have to take care of. So
yeah, that makes sense. So this is from the right.
Well, one second, we aren't replicating. Remember, we're writing. Like that write is happening, and I know it's a nuance, but it's actually pretty important, right? Because anybody can replicate it. This doing distributed consensus, even in a single data center, is difficult. Doing it like Germany, London, and New York, and dealing with that speed of light, the physical nature of data, I think that's one of those things that gets really, really tricky. Sorry to interrupt, but yeah.
No, that was a good point. So replication usually might mean that asynchronous replication.
That's right. Yeah.
Actually creating a replica, but since here everything is just active replica, so it's like a write.
That's right.
3 places. So that makes a lot of sense.
Yeah.
So I inserted a row. Now I want to read it, right? So how does read work, and what are the trade-offs there?
Yeah, so reads, look at, like, I think this is one of those differences, and we can talk about the difference between NoSQL and relational databases.
Yeah.
Again, the RAF leader understands exactly what's going on in that replica set, and that's up to, what you want to do. And so if that RAF leader lives in Germany, but I'm here in London, well, I've got to go to Germany to get that data. But why couldn't I just go to a local node to do that, right? Like, and so in the traditional model of what we did at Cockroach, you always had to go to the RAF leader, and placement of that RAF leader is important, and we can allow you to control how you do that as well. It's part of the language. This is what I meant by, like, you have to change the SQL side of things. Like, we had to give you SQL commands to alter table to change how those things work.
Yeah.
And so when you have to go to the leader to get that data, but we actually have a feature, it's called follower reads, where you can go to any one of the followers. So you can relax the constraints so that maybe the data might be not correct, but that's okay for that query. It depends on what you're trying to solve.
Okay.
And so, could I go to a follower? Like, because there's the leader and then there's the 2 followers. You could. It's a follower read. It's just syntax of your query to actually do that.
Yeah.
And you relax that constraint around the isolation and the consistency of the data. You might get stale data, but if you want to be guaranteed that the data is correct, go to the RAF leader and just run a straight normal query, because we're going to guarantee that isolation level.
Okay, interesting. And so this clarifies what happens on the background. But let's talk about the modeling part of the data, right? So I am writing like a relational data. So I have my name, age, and location, and then does CockroachDB also has like a relational model, how it stores the data, or it is changed under?
Well, again, top down from the developer, just looks like a relational data. It looks like a table. And nothing changes. Nothing changes. Now, underneath the covers, what we're doing, and this is not exposed to the developer whatsoever. But the way we actually stored it is disk, and there's several different systems that use this kind of model. We actually convert the data to KV, and we're actually using key value pairs to actually store the data. Now, there's a lot that we like. This is to me, once I understood how this works, it really started to help me understand really how Cockroach is special. And by translating kind of the relational form into KV at the storage layer, what we're able to do is basically take every table and create this kind of like monolithic, lexicographically sorted KV pairs. So, your last name starts with A, and you say that's the primary key on the table for name, and your age is just a column, and then there's location, which is, say Germany, right? And so basically each one of those values, your the primary key is used as the K in, say, the KV. So apte, and then age apte, and then your location. Okay, so then there's Walker and and then there's Walker and my age and Walker and London, right? And so it's ordered. Everything's in order. And so choosing the primary key on a table is really important, because ultimately, okay, let's now blow that out to a customer table with 100,000 records. Whoa, that's a lot of KV pairs. What we're doing is we're taking this big, like lexicographically, this monolithic lexicographically sorted KV set, and we're breaking it down into these 512 megabit chunks of data. Boom,
Okay.
boom, boom, boom. Think of them as shards. We call them ranges. It's all automated, but it's all sorted. And so what we have is we have this like B tree that sits in front of all of it, and we're able to find that data very quickly.
Yeah.
And each one of these ranges, like this, like, it's like 100 records at a time, 100 KV pairs at a time. That's a range. And basically that's the replica set. That's what we're writing 3 times, right? Like that's what we use RAF to manage these chunks of data in this KV store. And what that gives us is this really efficient way of either finding that data, updating that data, or you're doing very efficient, like the efficient get and put that you get in a KV store. And then we could translate that all back up into traditional SQL. And so this is what allows us to do this kind of automation of sharding.
Yeah.
But it's not really sharding because we're actually writing things in triplicate and all this other stuff, right? So it's fairly complex at that layer. But ultimately, that is kind of what it's doing. I was kind of going down a rat hole. Did I answer your question? I hope I went there.
Think, I think you did. And so I have a question. So you mentioned like it's like a size of a range, which is like 512 megabytes.
512, yeah.
512. So how like why this size? So what is the importance of this specific size? I'm just curious.
So great question. So about 2 years ago, the size of our ranges were 256 megabytes.
Okay.
And we changed it to 512. You can change it, I believe. I believe it's a set in the database. Don't quote me on that. I've never changed it. So, but it allows us it gives us like this very efficient way of moving data around. It gives us this very efficient control. Like we've learned over time, like what is the size of the range that gets us like efficient movement of data and efficient like placement of data in these chunks like this, within each one of the and the placement is. And so it's really about kind of reducing the overhead, yet optimizing the time it takes to actually get that data.
Okay.
It comes back to like, as we started to expand the size of the databases that we were implementing as a company, we learned a whole lot, like, because, we were doing, hundreds of tables with, say, a terabyte of data. As you get like into multiple terabytes of data, how do you get even more efficient in how you move the data around and how you actually transact and deal with that? Think about the efficiency of a B tree, KB, right? And like, how deep do you want that B tree to go? And how do we amortize the overhead of moving data around? Or because sometimes we have to split ranges, right? Like a range gets too big, I have to split that thing. We have to compact ranges back together as well. And so how do we get really efficient? So, we came back and, I think we changed it from 256 to 512. It was about 2 years ago. But it was ultimately a performance consideration within the database. And it's really low level stuff, but it was really amortization of how do we actually move this data in a very, very efficient way.
Yeah, that makes sense. And I have some other questions on this, but let's move to the other part. So I have inserted a row. I'm able to read that row because I understand how it is stored. As a developer, I don't need to, but now I do. I want to modify my location, so I moved back to India, and I want to modify the record. How does updates work?
Yeah, so updates work the same way as a write. Honestly, like I think of writes and updates as the same problem. The only difference is that you aren't updating and finding the place in the KV store to put your data. You're just actually finding that. So you're doing a get, right? Like one is a put, one's a get and a put, right? Like so the operations underneath are slightly different. But I think of reads and I think of writes. Now you said something that's very interesting though. You talked about like you moved back to India.
Yeah.
Okay, so wouldn't it make sense for your data to live on a server that lives in India so that you have very fast access to that? Maybe like all 3 copies of your data live in India so that all your transactions are super, super fast. Maybe I want 1 copy of your data to live in India, 1 to live here in London, 1 to live in Germany so that I can survive the failure of, say, the whole like, Europe West goes down and like, oh my gosh, like I still have 2 copies. Like,
Yeah.
so Cockroach, we have this feature called Geo Partitioning. And what Geo Partitioning allows you to do is at the table level, so at the customer table, we can define that, all records that have a location of India are going to live on India's servers. And the way that works is like, if you think about your name, Apte, right? Like what we do is we compound the location with your name. And if we think about that, like, okay, great. Well, we'll put the location in front of your name, right? I'm sorry, it's backwards. And so like, think about this as a sorted KV pair. Well, all the records that have India in the very beginning are going to be together. And then here's all the names. And then here's all the UK. And here's all the names. So now this remember the sorting of the KV?
Yeah.
All of the records that are for India are all going to be in ranges together.
Yeah.
And we're just saying, hey, look, take those ranges and write those data on servers that are named India.
Okay.
And so in Cockroach, we're able to actually do this. It's a very special feature. It's awesome. It is awesome, honestly. Like, once I saw that, this is one of those things, once you see it, you can't unsee it. But we're doing it at the table level. Okay. And so when I do this update, well, I'm doing an update on, so the developer, it just looks like an update.
Yeah.
There's a lot of things that we can do to speed the performance, because look, I'm talking about a database that's spanning India, Germany, and here in London, UK. What's the problem we have here? Speed of light. That wire is only as fast as that wire is going to be. We cannot beat that. So maybe I want all 3 copies of your data again to live in India. So I have very, very fast access to that data. Again, at the table level, we can define that, or we define, hey, I want resilience. I want to be able to survive the failure of the region going away. And so for each table, you define what your goal is for that. Remember that physical layer?
Yeah.
Understanding where data lives. That's what's important. And it's in the database design. I think on day one, for a developer, you just want SQL.
Yeah.
But once you understand these concepts, once you become familiar with Cockroach or a distributed database, you start to think differently. And this paradigm shift takes over, and you start to think differently about your query. Think about your update, right? And so let's do an update of 1 record. What about an update of 10,000 records? How do you think differently in that query? Well, if I have a distributed system, do I want to go against 1 node, or do I load balance that across 5 nodes? Yeah. Because each one of those nodes is an endpoint. Every node in Cockroach is an endpoint and can take a query. So maybe I distribute that so I get the parallel processing of the database to work to my power. It's one of these things that once you get used to the database, once you understand how it works, it gets more and more powerful every day. But sense. To the casual developer, go use our serverless version right now. Write a query, man, and like it's just going to look like Postgres to you.
Yeah. I think that's really powerful, because from the developer, it's all abstracted away.
That's right.
This complexity, we don't have to think about it.
Unless you want to. You don't have to think about it unless you want to, right? Exactly. Right. Yeah.
Exactly. I'm curious about what happens to the existing row. So I had a key value entry for, let's say, Apte, and then age, and then Germany, and then that row still exists because I'm not mutating that data. So is it deleted because of some compaction, or it's still there?
Yeah. No, we actually keep all the data so that you can do things like select data as of time. So you can do these kind of time travel queries as well. I want to see your record as of 3 days ago, and I can do that select, and so that's a select that you have. We also have a feature called for each table you can define time to live. So maybe you do want data to live only 3 days, and then you get rid of it, and the database will delete it and compact and do all your stuff. And so there's a lot of kind of knobs and dials around what you can do there. But yeah, we don't actually delete the data. We don't overwrite the data. We actually just append a new row, basically. Okay. But yeah, it gives you, again, this is one of those things. Oh, wait, I could do kind of this time travel query on my customer table. Cool, awesome. So now I have that as a developer. I have this, and remember, this is just one of those things, man. Let the database do that for you. Don't code that.
Yeah.
Why would we have, don't code that? So certain databases do that, and so we do that.
Yeah, makes a lot of sense. So cool. So I have TTLs, so I can set some TTLs per row. Is that correct?
Yep.
And
Yep.
so I can get my data deleted whenever I want, but I can also do these historical queries, like how the value has changed over time in last, let's say, few months. So that is another interesting query I could write with this. Um, and with this, so we little bit talked about also the replication or geo distribution of the data, and we also touch base. So I'm just trying to summarize what we have talked about.
Sure.
So from a developer's perspective, it's all plain SQL, and then the database is able to transform it to let's say a key value store, keeps it sorted, lexicographically sorted
Tough word,
format,
isn't it?
and it's a tough word, yeah. And and then it split automatically into these ranges or shards in simple terms, and these shards are like 512 megabytes, and then um, this size is just to make that performance better, and it's like a sweet
Yep.
spot. This might also change in future, I don't know, but this is the current size. And as a developer, I don't have control on that, right? Or I don't need to have, maybe.
You know what? That's a great question. I don't know. I think you can change that, but I don't. I don't know. You know what? I got to tell you, our docs are amazing. So, like,
Yeah.
if we just went into docs right now and searched for it,
Yeah.
you would, yeah, you would find it pretty easily. So that team does a great job. So, yeah, I don't know exactly. I've never dealt with it. I've never played with it, dude. So, yeah.
Yeah, it's totally fine. And then I think we also talked about raft, like how
Mhm.
writes happen and how it creates a consensus. And while reading, you have the ability to read from a follower and not the leader, but there's a trade-off with consistency. Do we also have tunable consistency on writes?
So, no, in Cockroach, we have implemented serializable isolation in our
Mm.
database. And serializable, if you don't know what isolation levels are, again, I'll send everybody to a website. Go look at jepsen.io/consistency. What Kyle
Mm.
does at Jepsen is awesome, Mike, and he looks at all these distributed databases and all these things. And so, but it's a great website. I send people there all the time to talk about isolation levels.
Yeah.
Isolation levels are basically, not all transactions in every database are guaranteed to be correct, y'all. Like, I'm sorry, but like, hey, developers out there, like, this thing called recommitted. Like, there's like
Yeah.
different levels of isolation, and I can, if you're writing data at the same time as I'm writing data, KB, like, and they happen at the exact same time, which transaction wins, and so like
Mm.
in serializable, what you're doing is you're saying each transaction has happened in order, serial, and so
Mm.
basically they happen in order in terms of what time they came into the system. This is, remember I was talking about clocks and clocks being syndicated, synchronized
Yeah.
across the thing. Well, if they all come in at different system times, it's hard to make them serializable. So
Yeah.
that's where we get the clock thing to happen. And that's a whole other topic in itself. But like, we implement serializable isolation by default in our database. I like that we did this because I think it takes away even the concept of a setting from the developer. Developers don't know what it is anyway. So let's just say,
Yeah.
hey, look, the transaction is going to be right. Can we relax that in some way in our code base? I think we have a reasonable understanding of how we might relax that.
Mhm.
But ultimately, I think that's really kind of what we have in our database, and it's going to be guaranteed that data is going to be correct.
Mm.
Now, what are the trade-offs there? The trade-offs are, well, you're going to get a couple more like transaction conflicts, like because you're going to get more transaction retries because you're going to have these conflicts.
Yeah.
I think there's probably there is like a small performance impact, but honestly, I love that we actually chose to be serializable isolation because it has forced us to optimize the performance underneath the covers as far as we possibly could. Now, there's some really interesting things we've done within distributed transactions from a software engineering point of view. We have 2 Sigma papers that were published over the past couple of years. One was actually, I think one is being published right now. That was like talking about a multi-region database. The other one, we talk about our transactional model. And if anybody's looking, like, look up Sigmod, Cockroach Labs, and you'll find this paper. We get into this thing that we did called parallel commits, and parallel commits is really, I think it's amazing what we've done. Basically, it's like, hey, look at when I'm doing a distributed transaction across broad geographies, like I'm doing one here, one in India, one in Germany, I have to get consensus. I have to get these 3 writes to happen at the same time. Well,
Yeah.
What I'm going to do is instead of like doing the first part of the transaction here, sending it to Germany, they do the first part, come back, second part, third part, like, because a query in SQL gets broken down into like lots of different steps. If people don't understand what a query plan is, it's actually interesting stuff. There's things called cost-based optimizers in databases, which think about, what's the cost of running a query? Because not all queries are the same, man. Like some of them are really, really complex. And so we do something called parallel commits. It's just really, really cool, where we're basically saying, hey, let's commit everything around this transaction on one node. And let's look at the data around that at before and after, send all of that to the second node. And the second node just says, hey, I'm in the same state? Yeah, great. Send back, yeah, I'm good. Back to the original transaction. It says, great, to the leader. And the leader's like, great, 2 of 3 have committed. Take away this kind of like temporary marker and say, great, let's go. And so that's kind of how that works. And so there's some really, really interesting advances to actually get really amazing performance out of the database at the transaction layer for that. But really, ultimately, we have implemented serializable isolation, and that's what we perform. Again, we're not building the database of like yesterday. We're trying to say like, look at in distributed systems. What are the problems we have to solve for? And so starting with this kind of like guaranteed consistent data, and then optimizing underneath the transaction layer to really get high performance, low latency transactions. Great place to start. Now that we're advanced, now that we have hundreds of customers, lots of people using this, is there a way to relax that? And so we're thinking through how we might allow people to change isolation levels in our database.
Yeah.
But the nice thing about it to developers is you're guaranteed consistent. You don't even have to think about it, right? And so it's not one of those things. So, or maybe you do want to think about it. And so it's a preference thing. But yeah, we are serializable isolation from the isolation level. That I in ACID is important.
Yeah, and I think it's sort of the gold standard for all the isolations. Like serializable isolation, having that kind of guarantee is really critical. And in some cases, it's so easy to reason about when it's like serializable isolation. So that makes sense. I just want to go back a little bit on the writing part. So the way it works, let's say in some NoSQL databases, they use something like consistent hashing to write the data, right? But here we are not hashing on the key, but we are just like in a sorted manner, we are appending it to a range. Does it help mapping it to a SQL query, or so? What does it give to us?
Yeah, so I mean, the same way you think about like how we hash things and then store them in the NoSQL databases, we're kind of doing the same thing. I mean, remember I was talking about like, your name and the location? Well, all that actually gets broken down into a hash. I mean, we basically actually encoding that so that we have these very, very fast access from the KV side of things. Like, one of the beautiful things I don't think people really understand about Cockroach database is like, we actually implement JSON as a native data type in here too. So you wanted to actually make this JSON, you can actually do that. You know what I mean? But like, and like if you wanted to have KV where just like the hash is the primary key, great. Like you could do that too. But we're actually doing that underneath the covers to speed access to that data. I mean, this is kind of one of those, it's actually very similar at that layer. It's just the execution layer where things get really different. From how do you have a transaction on a document model? And how do you maintain referential integrity in the document model? It's an overlay. For us, it's kind of native because we're basically translating that between the storage and the execution layer. So, but we're doing a lot of the same sort of things to speed access to that data on disk throughout the entirety of the distributed system.
That makes sense. You also talked. So I want to go a little deep into the distributed transactions, like how they are handled in CockroachDB. I think you mentioned briefly how it is done. So let's go into distributed transactions. So how do they work, and what happens if something goes wrong in a transaction?
Well, things don't go wrong, first of all, right? Because we're gonna ensure they're gonna commit or not, right? And so it's like and the beauty thing is we don't have like rollbacks like we we use something called MVCC. So there's something called multi-version concurrency control. And so if again, I like to direct people at sites that are just available, like the Wikipedia entry on MVCC, multi-version concurrency control, is pretty good.
Yeah.
And when you execute a transaction in Cockroach, there's like a timestamp of when a transaction happens. When we write data, each object has a read timestamp and a write timestamp. And basically, what I'm saying is like, hey, object, I want to write this data, and it says, okay, is your timestamp greater than the read timestamp? Yes, great, read it. If your transaction is coming in before like the read timestamp is up to date, then you can't, right? Like there's a problem. There's something is going on. But for each object we're trying to write, we create a temporary object for these things, and they're basically think about it as like a marker. I want to make these changes. Temporary object copy of that data. And so when everything goes right and no transactions come through or anything, nothing goes wrong, these temporary objects basically get committed as like the full-time object, the primary, basically. Think about that. And so there's no kind of rollback. There's no like, hey, I changed things and I need to make it back to the version. No. We're basically, for all three copies, we create these temporary objects. And when the commit happens, we convert the temporary objects to basically what it needs to be and say, hey, the transaction committed. Yeah. And so the things that can go wrong in a traditional database at that layer are different in a distributed system. Yeah. And this control over when things happen in the system, like say you write a query against something that I'm actually performing a write on. I have temporary objects out, I'm doing all this work, and you come in and say, hey, I want to actually update that record. I'm going to say to you, like, look, you have to wait until I'm done, or basically retry. You have to come back and try again because I'm busy. Yeah. And that's what MVCC does. It basically is like going to the store and there's one teller and everybody's in line. And each transaction happens, and how you got into that line, it's like, it's first in, first out, right? And so basically that's what MVCC is doing.
Yeah, interesting. Yeah, I think that makes a lot of sense. But since we are dependent on the timestamp, I think some accuracy of the clock matters here, right? So what is that accuracy, and what happens if a machine goes beyond that accuracy level? What happens there?
Yeah. So awesome question, and actually, at kind of the center of understanding distributed systems is time. Yeah, it's one thing that can't be off, right? And because that's what's important. And so I was talking about Spanner. Spanner uses atomic clocks, which keeps each of the nodes, I think, within like 5 milliseconds or something, 10. I don't know the exact thing. It's a really great blog post that actually talks through what we've done with how we do this without the atomic clocks. Mm-hmm. And basically what we've done in Cockroach is we've taken like NTP, which is Network Time Protocol, which is like old as the hills. I think it was like 1987. It was like kind of a standard thing. And so we're using that combined with this kind of like logical drift algorithm that we built. So for each node, we're using NTP and this logical drift to basically keep things within, say, 50 milliseconds or 100 milliseconds of each other, so that we're in basically an acceptable time frame. And then each node is basically monitoring, basically within the entirety of the entire system, the entire distributed system, basically how close it is to the rest of them. And so it's a very chatty protocol to actually understand how close things are. And if things get too far out of drift, basically we reset them. Okay. And so, the system itself has to take care of that. Yeah. Because you're right. That's what's important. Time is extremely important when you're dealing with consistency of the consistency model is dependent on time. And so we're using basically full software to do that as opposed to the hardware atomic clock. And that's one of the differences between Spanner and Cockroach, actually. But again, you have to run it on certain hardware. And so there's certain Spanner nodes you have to run on in GCP. They're great. They're optimized for it. They're awesome. For us, you can run Cockroach really on anything.
On any,
And then we'll synchronize clocks within the system.
Yeah, that makes sense. With this, let's talk about the fault tolerance part of CockroachDB, right? So first of all, let's say how CAP theorem applies to CockroachDB.
Yeah.
What happens when there are network partitions?
Yeah, so cap theorem is interesting. If anybody's not familiar with it, again, like there's lots of articles out there. I don't have a great article about cap theorem. I don't have a link like the others. Sorry, Katie. But yeah,
I
partition
can add all
tolerance.
those links.
Exactly, right? Like
Yeah.
partition tolerance is the thing that's special in cap theorem, right? It's like it's basically
Yeah.
in a distributed system, when things fall apart physically, what happens?
Yeah.
And you can optimize around two things: consistency of data or availability of the system itself.
Yeah.
And Cockroach is absolutely implemented as a CP database. Like we're going to guarantee consistency of that data no matter what, even if things fall apart, like the hardware networks fall apart all the time. Regions go away. We're going to guarantee consistency of the data. Availability is saying like, hey, look, at ask any node, I'm still going to have access to the system. I'm still going to be able to get data back.
Yeah.
And so we are a CP database, so consistency and partition tolerant, whereas a NoSQL database is AP.
Yeah.
Like the difference between the two sides is really this: like having a range of availability is what's important, right? Because we're 100% consistent, but we have this range of availability. Can we get you to 5 nines? Yes. There are a lot of dials and levers and things you can configure in the database. How many times do you replicate that data? How many nodes are in the system? How many regions does this live in? How many AZs do this live in? Like there's a lot of ways you can actually design the database to get really, really fault tolerant from an availability point of view. There's a lot of things you can do. When you come at the problem from an AP side, you solve like you're 100% available. How do you tune the consistency level?
Yeah.
That's a different challenge, right? And so tuning a consistency level means you're going to have eventually consistent data sometimes. And so when I think about the cap theorem and the two sides, but there's there's the agile nature of the AP databases, and it's super simple, and I totally get that. Whereas the other side, we're going to be guaranteed correct data, you get referential integrity, and you're getting there's trade-offs between the two sides of the cap theorem, and we're absolutely like CP. So I really got deep into cap theorem there for a second. Did I answer the original question? Sorry, I was going down a rabbit hole there.
No. I think you did. So the answer was that CockroachDB chooses to be a CP database, as opposed to an AP database. And I think you also mentioned like a very critical point. Like people might confuse the availability mentioned in cap theorem with high availability, as you mentioned, like 5 nines of CockroachDB. So being CP does not mean it is not highly available.
That's right.
Right. And that I think that is also very clearly mentioned on Cockroach Labs resources. I think some section I've read it somewhere, but I'll attach a link to it. So, what are your thoughts on that? Have you seen this confusion happening?
Dude, all over the place. People think it's binary. Like it's not. It's like, okay, you're binary on one, C or A, and then the other is a range. It's and so. That's the funny thing about the cap theorem. I don't think people really totally once you understand it, you get it. But there are people that are new to the cap theorem don't totally understand. Oh wait, it's a range on the other side is what that is. It's a very. I thank you for double clicking on that, because I think it's actually a pretty important point. Because as we all design our own systems as software engineers, and you think about the cap theorem, what does that mean for your own system? Not just look at we are applying the cap theorem in the database, and yes, it has a lot to do with the database because we're dealing with data. The cap theorem applies in your application.
Yeah, makes sense.
Like it does. Understanding Raft, understanding the cap theorem, understanding MVCC. Yes, we use them in the context of the database. Are these things applicable to you in your business application? And I think understanding these concepts is what helps people really understand distributed systems. We can abstract that all away and say, hey, look, just use a database that's doing this. But ultimately, if you start to use those principles up the stack into your code itself in your threaded language, you're using Go, you're using Rust, these things are applied in that layer as well. So as software engineers, as developers, starting to understand these concepts, I think helps us understand the problems we're trying to solve and the things that can go wrong.
Yeah, absolutely. And that is a very important point. So what happens? So how does the cluster of CockroachDB heals itself? So what are some mechanisms used there? So what happens? So I was just reading a blog, and it mentioned that there are different levels of resiliency you can set up at the table level. Correct me if I'm wrong. But it's like disk failure, then machine failure, and then a rack failure, data center failure, and the region failure. And all these resiliency models can be controlled by a developer at the table level. Is that correct?
Yeah. Yeah, it really comes down to, I think of these things as failure domains. What is your failure domain? What do you want to be able to survive? Remember, there may be trade-offs of latency of the query. Remember that. Like, that's a really important point, because when you start to think about the physical layer of data, what are you worried about? Survival and latency. So there's always trade-offs. And so your failure domain really comes back to like how granular you want your data to be, in terms of like, if I want to survive the failure of an AZ, okay, great. Then I have 3 copies across 3 AZs in a single region. Awesome. If I want to survive the failure of a region, well, maybe I have 1 copy in 3 regions. Or maybe I have 5 copies and I have 2 copies in one region, 2 copies in another, and a third in another region. Or maybe I have 7, right? Like, and so the replication factor, and that's tunable in cockroaches, actually pretty important to understand too. And so there's like that's what I meant by there's a lot of like, dials and levers you can kind of change it to play with the database. And so it's more advanced. It's once you get used to those concepts. But you can basically at the table level define where data lives. And that's a table level, not the database, which is different than other distributed databases, at the table level. Because, for the customer table, I want to make sure I have low latency access to that data, which means basically like I want your data, all 3 copies, the replicas, I want them to live on German servers. Great. You have this like the wire is super small relative to coming here. Great. However, for the inventory table, I want a copy in all 3 regions across Europe. I want a copy here in England. I want a copy of the Nordics, and I want a copy in, say, Berlin, so that if one of those regions goes down, I still have an inventory table.
Okay.
And so you'll have different goals for different tables, and that's this like the topology. What do you want to actually accomplish with that data? Is really what gets important. And remember, you have control over these exact things: the failure domain. A node, a rack, an AZ, a data center, a region, an entire cloud provider. Because we can actually have a single logical database running across like multiple cloud providers. We have customers today who have like one single logical database on different hardware in 3 different cloud providers. That's awesome. And so like, so can I survive the failure of an entire cloud provider going away? That's a failure domain for us. Could I do an entire Kubernetes cluster? That's a failure domain for us. It really comes down to each table and what you want to survive.
Absolutely. I think that's such a great flexibility to have, and for me to decide, at the table level, how do I want to survive and what kind of failures I want to survive, right? So that's really awesome.
And then being able to change that in production, like literally, simple CDL, like we just basically alter table and we could change these things for that particular table. Like say we bring on a new region, we bring on India, and we didn't have any of my data there, but I want all my customer records to actually go there. We do an alter table command, and all that data is now going to live on those new servers without any downtime. That's awesome.
Awesome. I just have another question on the geo distribution, because it came to me suddenly because I was working on a use case where we wanted to, make the data available because of compliance reason within the boundaries of Germany for customers who want that way. So let's say I have like a existing database on CockroachDB, but I don't have like a location field anywhere in the table, for example. But I now want to migrate that data some way to, let's say, only Germany. How easy it is to do it? Like, is it even possible?
If your data doesn't tell you where the data needs to live, you can't do it.
Unless you could scan it or something, right?
I mean, like, the data's got to self-identify that it needs to live on German servers, or at least live on UK servers. Like, I can't like have some premonition or ESP, like, you know what I mean? Like, the data's got to actually identify itself. But we can do that, like for like these kind of like privacy regulations or just like compliance stuff. Can we help with that? I have all my data lives in certain places. People like us for that reason as well. So
that makes sense, because we had the same problem. We didn't have any identifier because that data was like existing from forever, and we didn't know that we wanted to implement such a thing. So I think it's very important to think about the geo distribution right from the beginning. And does it make sense?
Yeah, and design your data around that if you need to. Yeah.
Let's talk a little bit on the deployment models of CockroachDB. So I read that you can deploy on a dedicated cluster with like Cockroach Labs managing it. You can also have serverless. I have specific question on serverless. So I'm always confused when I think databases and the serverless model together. So how does that work, and when does it make sense from the cost perspective?
Look, at serverless is a consumption model. There's things that we had to do in the database to make it serverless, because taking the serverless concepts and applying it to your software is what's important. Saying and that's for all of us. I don't care what you're building. Like taking the serverless concepts and applying it to what you're building, I think is very, very interesting. And that's what helped me start to really understand the value of serverless, right? Like to make things multi-tenant, to make things spin down to zero when I don't need them, but to come back immediately when I need them. To put a rating engine on them so I can only pay for what I consume, right? Like those principles of serverless, when applied to the database, are pretty interesting. And, we released the beta of our serverless deployment model, it was a couple months ago, last fall. And, basically what it's doing is like, hey, here's a database that's going to be geolocated and all these things. Right now it's single region. So it's basically like an instance of Postgres that you get immediately and you don't have to pay for it. Like it's 5 gigabytes of storage, 250 million request units a month, which is an abstraction of queries, right? So it's ample, right? And so being able to do that's great, but ultimately I think people are interested in it is because you're only going to pay for what you use, right? And so this consumption model, like, do I want a managed service that I have a dedicated cluster that I have 5 nodes or 10 and I have this strict control over who has access? Or do I want to live in an environment where I'm just building pretty quickly and there may be other people in there and we're able to firewall off data very well. It comes back to, remember I was talking about that KV sort? Remember I said like, look at here's all the country data and then your last name. Well, what if I put a tenant ID in front of that? Now I'm lexicographically sorted. All the tenants are in the same, all your tenant range, all your data is in the same ranges, you know what I mean? So like we're able to like firewall off stuff. And then we use Kubernetes to spin things up and down really quickly. We have hot nodes that aren't assigned to tenants. And so we can scale compute. We can scale transactions separate from storage. And in so doing, what we've done is we've created this consumption model, like where I just pay for what I use. We have a spend limit on that. So like I'm never going to pay more than $10 a month or $100 or whatever it is. And we're just going to basically throttle the amount of transactions so you still have service for the rest of the month. It's consumption. Serverless to me is about consumptions. It's about optimizing what I'm paying for from a compute point of view of what's going on. Some people want control, and you just want a managed service where I have like complete control. I have my own nodes, my own everything within the concept. So it really comes down to kind of your preference of consumption, and it's a deployment model. Still the same database.
That clarifies a lot of things actually. So yes, I think I have only one last question.
All right.
What is that use case when CockroachDB is not that great as of yet, and maybe in future it will be?
Yeah, that might be one of the best questions anybody has ever asked me, because it's funny. Like I get salespeople asking me all the time, "Oh man, what's a Cockroach good for?" I'm like, "Well, it's a relational database, dude. Like, what's a database good for? What's a relational database good for? Well, everything. I think different workloads demand different things. And are we good or bad at certain workloads? I'm not going to comment on that like as much, but then it's up to you as a developer to understand your workload. You have an application and you're trying to solve something. And, maybe you need like super fast access to data that's like all the time, and it's okay if like it's not synchronized all the time between, maybe you're using Redis for that. Or maybe you're like, you understand the pattern of access to that data and you're using a document store because that's right for exactly what you're doing in that part of the workload. When you have a system of record and you want like, operational transactions, that's where a relational database comes in. So you still think of that. Are we good for global? Sure. We're really good in a single data center as well. Like the operational efficiency of managing that database, active, passive, sharding, that's going to happen in a single region too, dude. Like the business continuity that we can give to people, guaranteeing uptime. both plan and against plan and uptime in a single region for a transaction operational database. There's nothing like it, and so it's a great question. I don't know if I answered it exactly because I don't think there's an exact answer. I think it comes down to what your workload is and what you're trying to accomplish. And different workloads have different requirements. You got to understand your requirements, what you want.
Yeah, I think that makes a lot of sense. There is no silver bullet, and there are some trade-offs that you have to make, and depends on the use case. Cool. So I think you have answered all my questions, and you have kind of sparked a lot of curiosity, at least in me. And I'm pretty sure all our viewers are going to be more curious on understanding distributed SQL and primarily CockroachDB, how it works after watching this podcast. So I thank you for your time, and
awesome.
I really enjoyed our discussion, and I look forward to using CockroachDB, trying out certain things, and collaborate with you more. So
great.
Thanks a lot. Thank you.
Yeah, you bet. I hope I did a good job explaining some technical concepts. I hope we started talking about evangelism. I hope I did a little bit of like sparking curiosity in people.
Yeah, absolutely.
I hope that helped. Great. Thank you.
Thank you.